Hello everyone, welcome back. In the last lecture we were looking at squeeze states and we were trying to interpret them and what does it really mean physically and so on. If I were to summarize, in the last couple of weeks we looked at various phenomenological descriptions of classical and non-classical light. Okay. So firstly, we talked about the photon statistics and we said, you're going to have a histogram like this. If you look at the statistics of the number of photons that are there, that is going to exhibit a histogram, and then you will see that the histogram has a peak around the average value and so on. And then we also looked at the correlation functions. So specifically the second order correlation function, which is G2. So if you have classical or chaotic light source, then you will have G2 greater than 1 at time t equal to 0, whereas coherent you will have G2 equal to 1 and so on. And if you have sub-Poissonian or non-classical light, it will actually be even lower, correct? And then we also introduced in the last week, we introduced the idea of quadratures. Quadratures are essentially used to describe how the quantum states behave. So we talked about the vacuum state, and then we also talked about the coherent state and the squeeze states and so on. So I'll call all of these as phenomenological descriptions. Okay. The reason is we didn't really tell you, the underlying theory. We just described various states. We said, okay, this is what is going to happen. If you have this, this is going to happen. So it was more of a descriptive thing. Okay. But if you look at any of these textbooks, you will see some amount of theory that is applied, and if you want to work in this area, it is necessary to get a glimpse into that, or at least understand the terminology. We'll have to speak the same language. So this lecture and next 1 hour, 1.5 hours, we'll try to talk about the foundations of quantum theory of light. Okay, so it will be a little bit mathematical. But the mathematics is simple. I mean, you will be introduced to a lot of new terms perhaps, but I can assure you that once you accept the definitions and so on, the mathematics is reasonably simple. All right. So let's get started. The first concept I want to introduce is the idea of canonically conjugate variables. I call it pairs, but yeah, canonically conjugate variables. What do you mean by that? For example, we talked about the Hamiltonian, and we said the Hamiltonian is given by p square by 2m plus half m omega square x square. This is what I wrote, right? But why did we write this Hamiltonian? Why do we need a Hamiltonian? Okay, the reason for that lies in classical physics. So we all studied about Newton's laws. The force is, you can calculate once you know the position and the velocity and so on, you can and the forces that are applied to a system, we can compute the time evolution of a system at any point of time. For example, if you have a car, the forces that are applied, and then you compute the acceleration, velocity and so on. The same thing applies even for billiards balls. Let's say a car, maybe the equations are easy to solve. It's one big object. But let's say if you have to solve the trajectory of all the billiards balls on a table, how would you do that? So you'll have to individually track the position, velocities and the directions and so on. It becomes harder to do, correct? So once you have larger systems, it becomes difficult to apply the Newton's laws as they are given. So in the late 17th and early 18th centuries, various other approaches were developed. One such, the first one was called the Lagrangian approach, and the next one was Hamiltonian approach. Essentially, these are dependent on energy. So instead of solving for the positions and velocities, we will look at the energy, total energy of the system. Let's say in the case of Hamiltonian is essentially the sum of the kinetic and the potential energies. And we look at the Hamiltonian, and if you look at the time, and that's going to depend on various variables. Like for example, here we are talking of momentum and the position. So these are the variables that are contributing to the Hamiltonian. And once you understand how the Hamiltonian evolves over time, you can actually describe the system. So that's an alternative way of describing, and it makes life fairly simple when you have complicated systems. Okay. So why did I write the Hamiltonian in this form? Why shouldn't I write, let's say for example, the more common way would be instead of why not h equal to half mv square plus half m omega square x square. Why can't I write in this form? What is wrong with this? I mean, effectively we know that potential, the kinetic energy is basically half mv square. I can write it like this. I mean, it's equivalent, right? So the reason why, you always see the pair of p and x is that they form what is known as a canonically conjugate variable pair. So basically p and x form a conjugate pair. What do I mean by this? Well, it turns out that they satisfy the Hamilton's equations of motion. They satisfy equation of motion. So just like you have the Newton's laws, you have Hamilton's equations of motion. If these pairs satisfy, you can actually, there are some benefits. Okay. So what are the Hamilton equations? Well, there are two equations. The first one, if I take, if you're talking about the variables p and x, right? So take the time derivative of p, and that is going to be equal to the time derivative of p is going to be equal to minus dou h by dou x. Okay. Similarly, the time derivative of x is going to be equal to dou h by dou p. These are the Hamilton's equations of motion. Okay. So let's verify for a moment, whether the Hamiltonian in this form satisfies it. So what is dou p by dou t? Well, the change of momentum is essentially the force, right? And that should equal to dou h by dou x. That is basically minus is there, so minus h in terms of x. So basically it's going to be m omega square x. So effectively this is minus kx. So the force, Hooke's law, this is satisfied. Force equal to change, the change in the position with change in the Hamiltonian with respect to position. Similarly, if you look at the second equation, this is velocity v, right? That is equal to dou h by dou p. So if I take derivative with respect to p, I get p by m. So both equations now we see that they are satisfied. Okay. So if in the first case here, in the second case here, this is velocity basically, and this is p by m is velocity, and the first case force equal to minus kx, right? So when this happens, we say that p and x are canonically conjugate pairs. P and x are canonically conjugate pairs. Okay. Let's just take a moment and examine whether the other pair, if you take the other form, right, in terms of v and x, if you write it, for example, if I write my Hamiltonian as h equal to half mv square plus half m omega square x square. If I write it like this, will it satisfy the Hamilton's equations of motion? Okay. To check that, we'll first do, the same thing. Now instead of p, I should write dou x by dou t. Is it equal to minus dou h by dou x? Is it equal? To examine, this is basically velocity, right? This is velocity or x dot, right? V equal to minus dou h by dou x. That is equal to m omega square x, right? So obviously this is not going to be satisfied. It's not equal to, right? And the other equation is dou x by dou t. We did that already. Okay. Dou x by dou. Yeah, sorry, we did that already. Okay, come on. No, I made a mistake here. So I should do dx by dt should be equal to by dp, not dx. It's a mistake. So if I'm talking the first equation, instead of p, I'm putting x. So sorry, if I do this, I should verify whether dx by dt is equal to dou h by dou p. I should do, because it's this one, right? So this is velocity v, and the other one is now, okay, sorry, just a minute. sorry, excuse me. So now, previously we were, in this case we were talking about P and X. Now we are choosing the pair V and X. Okay. So if I do in terms of V and X, it should be dx by dt is equal to dx by dh by dv. Okay. This should be the variable V. So now let's verify that. So dx by dt is going to be equal to velocity here. That's equal to dou h by dou v is equal to m into v. So clearly this is not satisfied, correct? Velocity is not equal to momentum. The other equation will be, okay, there is even a minus, we didn't put that, but it doesn't make any difference. Okay. The other equation will be in terms of, again, dx dou x by dou t. We already did that. Since we already did this, let's do the dou v by dou t. V by dou t, that's equal to minus dou h by dou x, correct? Yeah. So dou v by dou t is acceleration, right? This is acceleration, that's equal to minus dou h by dou x will be m omega square x. So again, this relation is not true. So you will see that in both these cases, the Hamilton's equations of motion are not satisfied. Okay. So you might ask, how are you writing these equations? Well, essentially you have them in such a way that the change of momentum with respect to time is going to be minus of dou h by dou x. So instead of p, I'm putting v. That's it. I'm trying to replace the equations of motion in such a way that instead of p, if I consider v, what happens? Okay. And now you clearly see that v and x do not satisfy Hamilton's equations of motion. Okay. So they're not a conjugate pair. Yes.
What other conjugate pairs are there except for P and X?
I will come to it. Energy and time. Okay. So how do I know that? Well, I know that because there is a specific property they obey. Whenever they're conjugate pairs, there's a specific property. Okay. We'll get to that in a moment. Okay. So, but you might ask, so what? What if they're conjugate pairs? Okay. The reason that is useful is that it makes our life simple. Because, we eventually, what we want to do is we want to write the Hamiltonian for the electromagnetic field and we want to solve for it. We have proved in the previous lectures that light also behaves like a harmonic oscillator. And we know the Hamiltonian for a harmonic oscillator. Now, the question we ask is, what is a Hamiltonian for light in quantum picture, right? We want to know the Hamiltonian, let's say, Hamiltonian for quantum harmonic oscillator. Right? We know what is the Hamiltonian for the classical harmonic oscillator. Now what will be the quantum harmonic oscillator's Hamiltonian? And basically I have repeated it, essentially whatever I have written, okay, it's in the cleaner form. So you have the Hamiltonian for the classical harmonic oscillator and the canonically conjugate pair. So you have this Hamilton equations of motion that are satisfied. So if they are canonically conjugate pairs, you can actually simply replace x with an operator called x cap. Similarly, I can replace p by an operator called as p cap. I'll define what these operators are for a moment. For example, x is simply multiplied by x and p will be IH cross dou by dou x. Okay, the momentum operator. So wherever x is there, I'll put an x cap, and wherever p is there, I'll put a p cap. So now my Hamiltonian will become, Hamiltonian of a quantum harmonic oscillator becomes p cap square divided by 2m plus half m omega square x cap square. That's it. So I don't have to do anything. I just have to write it in this form. So I know my Hamiltonian now. All the effort of canonical conjugate pairs was only to ensure that you can write the Hamiltonian in this fashion. Okay. That's why every time you see any quantum optics textbook, Hamiltonian will be written in this form. All right. Make sense? Any questions? So now what are the implications of it? There was a question, saying that what are the other canonically conjugate pairs? I said that, okay, energy and time. How do I know that? Well, to do that, we'll have to understand a little bit. The short answer to the question is that they will have an uncertainty relation. If you have a conjugate pair, X and P, you will have an uncertainty relation. We studied Heisenberg's uncertainty relation as delta X into delta P is greater than or equal to H cross by 2. Similarly, there is an energy and time uncertainty. So whenever you have conjugate pairs, there will be an uncertainty relation between the two. There won't be an uncertainty relation between delta V into delta X. Okay? That's the thing. Okay? So now, what happens is, let's try to understand the implications. Okay, first of all, what is this operator that I introduced? I said that these are operators, right? Well, the operators are defined by these expressions. So if I have X, I'll simply, I'll take it as X only, and then I'll take P as basically the first derivative of minus IH cross d by dx. Okay, so an operator is something that operates on a wave function. That's the meaning. Okay, because in quantum mechanics we are dealing with probabilities. We are not dealing with the exact, we don't exactly know what the position is going to be. There's a probability of a certain, let's say particle being in a position, right? So what we are interested in quantum mechanics is always the probabilities, or what we call as expectation values. For example, if you ask me, what is the probability of finding a particle at this position? I can say there is an expectation value of X. That's it, at this position. I can't tell you exactly what it is going to be. Okay. So the way we, if you think about, let's say, the way we calculate that is in the language of quantum mechanics, we'll say that the expectation value of X is going to be simply going to be equal to, let's say, okay, let's take a wave function that is, in the region from L to L. Okay, so minus L by 2 to L by 2. If I take, I can talk of a wave function. Let's take an example wave function. Say that it is going to be 1 over root L exponential ikx. I'm taking a plane wave in a certain region of space which is of length L. Okay, minus L by 2 to L by 2. I have taken a plane wave. Now, if I want to find out what's the average of the position of the wave function, okay, so what I'll have to do is I'll have to take a wave function here, and then I have to do psi star x into psi dx. Okay, so basically that is my definition of expectation value. So if I want to find out what's the average value of x, simply wave function times x. So basically the conjugate of the wave function times x into this one. Or more generally, if I have to write it, any particular variable instead of this, maybe I'll first write that. So instead of it, I can write like this. Average value of a, operator a cap, is going to be integral over certain area or volume or whatever you want to call it here. So this is going to be psi star r, some psi is going to be some function 3 dimensions, a psi of r dr. So basically you have to integrate over that range essentially. Okay, so now if I have this plane wave in this region of space, minus L by 2 to L by 2, what will be my expectation value of position? Well, that's going to be equal to psi and psi star. I can just, there's going to be minus n in the exponential, otherwise, so 1 over L integral minus L by 2 to L by 2. Psi star is basically going to be exponential minus ikx x exponential ikx dx. So, and if you integrate it, it will turn out to be equal to exponentials will go out, so x dx, so x square by 2 minus L by 2 to L by 2, this is going to be equal to 0. Expectation of position is 0. So basically, if you have a region, in that region the position averages out to 0. No surprise. Okay. Similarly, what is the expectation value of a momentum? Let's say if I have momentum operator, right? If I want to know what is the typical value of a plane wave propagating, so now expectation value of momentum is going to be equal to minus, again, 1 over L minus L by 2 to L by 2, and this is exponential ikx minus ikx. So I'm doing it in 1 dimensions. So minus IH cross d by dx and exponential ikx dx. Okay, so minus IH cross comes out, and then what will happen? If you take a derivative of wave function with respect to x, I'll get an ik. So this is going to be equal to minus IH cross ik 1 over L exponential, this is dx essentially, dx minus L by 2 to L by 2, right? So this will be equal to, minus minus goes out, this will be equal to h cross k. So if I have a plane wave, the expectation value of momentum is going to be h cross k. That's why we define momentum of a plane wave is going to be h cross k without justifying. But it turns out that even the quantum theory tells you the same thing. Okay, in a region of space, the average value is 0 of x, but then of momentum is going to be h cross k. It's traveling in a certain direction, right? So now all this is fine. Now we are trying to simply lay the groundwork. It will become clearer in the next lecture. I'm trying to introduce various variables, and if you are not familiar with this, I'm just trying to recap. So now there's an interesting relation between the operators if you have x and p. Okay, one thing we have to see is, let's try to calculate x cap p cap acting on a wave function psi. Okay, x cap p cap psi. Okay, so the question was, if I take minus 0 to L, what happens? Instead of minus L by 2 to L by 2. Well, if you take 0 to L, I'll have to change my normalization as well. Yeah, because there is, okay, yeah, you are talking of wave only from 0 to L. So there is no negative component to cancel out. So yeah. So x cap p cap psi, basically, if you try to calculate, what happens? So this means that x into IH cross minus IH cross d by dx acting on psi, correct? This is what it means. So this is going to be I minus IH cross x dou psi by dou x. This is my first term. Okay. Now I want to calculate the opposite. Let's say p cap acting on x, p cap x cap acting on psi. I'm interchanging the variables. Okay. If I do that, p cap is minus IH cross dou by dou x, but this derivative acts on everything to the right of it. So this will be x times psi. Okay. So this will turn out to be equal to minus IH cross x dou psi by dou x minus IH cross psi. Okay. So what you will see is, if I have combination of these two, so the question is x cap p cap minus p cap x cap, okay, acting on psi. You might say that, oh, they are commuting. You remember what is commuting relation, commuting numbers or commuting variables. X into y equal to y into x. They commute. Okay. If I write basically xy equal to yx, means x and y commute. Commutative relations we might have studied, early in yours, sometime they would study associative property, commutative property, and so on. So if you have x into y equal to y into x, it's commutative. But here what you will see is x cap p cap and minus p cap x cap. These are operators and they're acting on a wave function, and you'll see that this is equal to, if you subtract the one of the terms, x d psi by dx will cancel out, and you'll end up with IH cross psi minus IH cross x dou psi by dou x, say minus IH cross x dou psi by dou x minus IH cross psi. So if I subtract, I'll end up with IH cross psi. Okay. So what this means is, this basically is represented usually, and the reason I'm introducing this slowly is that I'm going to use these expressions later on in the when we're describing the harmonic oscillator. That's why. Okay. So what it means is, we'll define a commutator bracket x comma p. Okay. If you have an commutator bracket acting on, let's say, we generally omit the wave function, and we say that if it is this is going to be given by x cap p cap minus p cap x cap, the operator, right? So what we say, if suppose this was acting, this commutator bracket was acting on a wave function psi, okay, if this was acting on a wave function psi here, you will see that this is again acting on psi. You know that it is IH cross psi. So basically what it means is that if you have a commutator bracket like this, x cap p cap, that is going to be equal to IH bar. This is an uncertainty relation. Okay, uncertainty relation exists between x and p. What is uncertainty relation? We can actually compute. Okay, so we have a basic theorem. We will talk about it later on if required. So basically, saying that if you know the average value and you know what is the variance, we can compute what is the variance. So variance in delta x into delta p is going to be what? We can do that. Okay. So basically, this is the fundamental concepts basically. So what we are saying is we have this canonically conjugate pairs. If you know them, we can write the Hamiltonian in a straightforward fashion, and we essentially have to talk about these operators. And those operators, what operator means we talked about. That's it. Okay. So now what we will do is in the next lecture we will talk about the Hamiltonian, and we will try to solve for the Hamiltonian. That's the agenda in the next lecture. All right. Thank you. Yeah.